Okay, go ahead.
Hello, everyone. Dr. Fatma Çiçek is to give us a talk today on Selberg's central limit theorem. And she completed her PhD in the University of Rochester in 2020 and was working at IIT Gandhinagar. And today she's going to give us a talk. Let's welcome her.
Thank you for the introduction. Yes, I'm very happy to be speaking here and talking to a new group of people. I have given a talk on this topic a couple of times, but mostly because this was the topic of my PhD thesis. So the plan of my talk is going to be as follows. So first, we need to see some basic facts about the Riemann zeta function. So and then we will see the statement of Selberg's central limit theorem. So Selberg's central limit theorem is a statement on the behavior of the Riemann zeta function. That's why. We also try to see how it is sort of related to the usual central limit theorem that you see in probability theory. Okay, it is reminiscent of that. We will also see some basic ideas in the proof of Selberg's theorem that was sort of influential for the further research. And at the end of my talk, I want to just give some variants of Selberg's theorem. So some different versions of Selberg's central limit theorem. And then if you have time, we will see an application. Okay, so this is the Riemann zeta function. So you might have seen this before. And you see where you have this simple looking infinite series, and this will converge absolutely when real part of S is bigger than 1. So you know the behavior of this function when you are in this half plane, and in the same half plane you have this so-called Euler product. So this is a product over the prime numbers, and you have this simple expression that follows from the geometric series. Okay, so the Riemann zeta function is important due to its connection to the prime numbers, and this is sort of the first occurrence of that. You may think in that way. And so this was in this half plane, but actually the things are not as restrictive to that half plane. So if you want to use some analytic facts, and you can see that the zeta function has a meromorphic continuation to the whole complex plane, and then you will only encounter a simple pole at s equals 1 with residue 1. Other than that, everything will be smooth. And one way that you can see this is this functional equation. Okay, so this analytic continuation, this is of course analytically important. Another important aspect of the Riemann zeta function is this Euler product. Another important fact is these symmetries. So with respect to the real axis, the values of the zeta function are symmetric. This is because on the real line, this function takes on real values. And aside from that, you have an additional symmetry given by this functional equation. This gives you a symmetry with respect to the so-called critical line when real part of S is 1/2. Okay, so this symmetry with respect to the critical line, this comes when you use this functional equation with the symmetry with respect to real axis. Okay, because this is the type of symmetry that you have when you have S versus 1 minus S, and then you also have another symmetry with S versus S, S to 1 minus S bar. So you sort of combine these two. And you see from the properties of your function in one half plane, you can deduce properties when real part of S is less than 0. So these are sort of the less significant regions. And when real part of S is between 0 and 1, things will be more tricky. Okay? And that's sort of where we encounter some important zeros of the Riemann zeta function. So this is sort of the picture that we have when we look at the complex plane. So due to the functional equation, we have some so-called trivial zeros, these green points, -2, -4, -6, and so on. These are the trivial zeros. But aside from those, in between this strip, critical strip, we have so-called non-trivial zeros. Okay, and so here they are denoted by rho in general, and so far we have only been able to computationally find or detect non-trivial zeros that lie on the critical line. Aside from that, we don't know even one zero that is not on the critical line. Okay, and we also have this notation where we denote the multiplicity of the zero with m rho. So that is some notation that I will use later on. And this is a very general notation: beta plus I gamma. Beta is the real part, gamma is the imaginary part. So the Riemann hypothesis, the famous Riemann hypothesis, tells you that these betas, they are always 1/2. Okay, so all those non-trivial zeros lie on this critical line. So you see, this gives you a very nice, uniform behavior. Everything is on one line, and this is a nice fact because in analytic number theory, most of the time things work well on vertical lines. Okay, so we also have some conjectures on non-trivial zeros, in addition to the Riemann hypothesis. So one conjecture is between these ordinates of non-trivial zeros. So you sort of have this pair correlation function that is given on this right-hand side when you consider the distance between these ordinates. Okay, so here gamma and gamma prime are ordinary ordinates, so they can be equal to each other. This alpha and beta are just some real numbers. So if you want to count, gamma and gamma prime that are distanced by these numbers, then you have this pair correlation function here. Okay, so there's a reason why you have 2 pi over log t factor here. I will talk about that later. So this 2 pi over log t is like a scalar factor that we need. But aside from that, you basically consider alpha and beta. Okay, so this is a very important conjecture. And the consequence of this is this zero spacing hypothesis. So usually when you use the zero spacing hypothesis, you also assume the Riemann hypothesis in the beginning, I mean. So this tells you that when you consider consecutive ordinates, so these, if you have a multiple zero, then these will be equal to each other. So you'll be having zero here. So these, when you consider the ordinates that are, close to each other by c over log t. So this is also in the scale of 2 pi over log t. Then this is, you won't have, when c is small, you won't have a lot of them that are, close to each other by c over log t. So the c over alpha, c is between 0 and 1. So this is going to be a small number. So you expect to have a small proportion of them. Yeah, as I said, so you can prove that this follows from Montgomery's pair correlation conjecture. The only detail here is that there's this parameter alpha. So this zero spacing hypothesis, this depends on alpha, but the strongest hypothesis will be when alpha is 1. So when you switch alpha on this interval 0, 1, when you make alpha smaller, you get a weaker hypothesis. So it just gives you an additional parameter in your theorems to control and make your theorems stronger or weaker. And yeah, as I said, this also follows from pair correlation conjecture. So it is slightly weaker than that. And so this simplicity conjecture. So the justification that we have for simplicity conjecture, so all the non-trivial zeros are simple, is that when you assume the Riemann hypothesis and when you assume the pair correlation conjecture, Montgomery showed that almost all the zeros are simple. So what that means is you look at proportion of zeros that are simple within all the zeros, then you get, asymptotically, you get 1. We actually don't know, if all the, individual zeros are simple, but asymptotically we know that, they have to be simple, but there's also a further hypothesis where you claim that all zeros are definitely simple, each one of them. Okay, so basically we don't have any other reason not to believe this simplicity conjecture. So Montgomery's pair correlation conjecture, that's something for the, the vertical discussion. Yes?
Can one say something like, even if there is no reason why the zeros there should be zeros of different multiplicity. Is that, that's something that...
Yeah, so we know that almost all of them have to be simple. We believe that by Montgomery's pair correlation conjecture and Riemann hypothesis. But that doesn't mean that, all the individual zeros are simple. But we don't, so that's not something that has been proven by other conjectures. But we also expect that should be the case because we don't have any reason not to believe that. Does that make sense? Yeah, so we basically don't have any reason not to believe a simplistic conjecture. That's why. Okay.
Well, can you give us a sense of a little bit, if you have time, Montgomery, can you explain a little bit furthermore Montgomery's pair correlation conjecture?
Montgomery's conjecture, yeah. So I will say a bit more. Let me show you this formula and then I'll say a bit more. So we have this Riemann-Formann formula where we count the number of zeros. So this n of t. So this n of t, you basically look at the zeros that have ordinates between 0 and t. So you are on the upper half plane and your ordinate is at most t. Okay, so you count them and then you get this counting formula for that. So you have this initial factor, so initial term, t over 2 pi log t. Okay, so that's the largest term. Everything else is smaller than that. And then you have this special term here, argument of zeta. So imaginary part of log zeta. And you put that into this function s of t. So you define this function s of t. Okay, so now this function n of t, this is a discontinuous function. It has jump discontinuities, right? So when t becomes the ordinate of a non-trivial zero, this side will increase by 1. Not by 1, sorry, by the multiplicity of that zero, right? So that means everything else is continuous here, as it is proven in this result. So this argument of zeta, this also has a discontinuity there. Okay, so this will make a jump by the multiplicity of the zero, and then you have this pi factor here. Okay, and it is defined in this way of continuous variation, so that you want to make your s of t to be continuous, at least when t is not the ordinate of a non-trivial zero. Okay, when it is the ordinate of a non-trivial zero, you sort of define it in a special way. But aside from that, it will be continuous in between two consecutive ordinates. Okay, and so about the pair correlation conjecture, so you see this n of t, this is of size t over 2 pi log t. Okay, so when you look at the interval 0 to t, that is of length t, so that means the average spacing between two ordinates is going to be about 2 pi over log t. Okay, because you have this many t over 2 pi log t zeros up to height t. So 2 pi over log t is the average spacing. So these ordinates are actually close to each other. And that's why you have this 2 pi over log t factor here. That's the scaling that you work with. And then you just basically multiply that scaling factor with alpha or beta. Okay, so you count the ordinates that are this close to each other, 2 pi over log t times alpha, 2 pi over log t times beta. And then as t tends to infinity, this is asymptotically equal to this integral. Okay, this delta 0, this is a, like a Dirac delta type term that depends on alpha and beta. So you need to sort of make a correction when alpha is 0, because when alpha is 0, you'll be counting gamma equals gamma here. But that's not that important. The important thing is this function 1 minus sine square over x squared type of function. Yeah. So this sort of tells you how these ordinates are spaced. Yeah. So it tells you something about the vertical distribution. Riemann hypothesis tells you something about the horizontal distribution. It says that all these real parts, betas, they are 1 over 2. But this conspires something about gamma minus gamma prime, the distance of the ordinates. Okay. This also is a nice connection to random matrix theory if you are interested in that. But that's not really my research area, so I won't get into that. So this function, the sphere correlation function, is a special function. Okay. Now, still we are in the background. So now, what is the usual central limit term that we have in probability? So what you have is some bounded random variables, and they have these expectations and these variances. Okay, and the statement is that when so let's say here, well, it's not, I believe it's not necessary, but let's say here we have independent random variables. I think we must have independent random variables, if I'm not mistaken. So in our case, our analog will be independent. So what happens is if the sum of the variances tends to infinity as n tends to infinity, so this is the critical condition here, okay? Then asymptotically, when you sort of normalize with the, by dividing with the standard deviation, total standard deviation, then you get the Gaussian distribution. Okay, so this thing on the right-hand side, this is the value of the distribution function of the standard Gaussian random variable. So this is, when the random variable takes a value in between A and B. Okay, so I'll use this later on. So basically, asymptotically, you have a Gaussian distribution, right? Now, the critical condition is that the sum of the variances has to diverge. If they don't diverge, if they converge, then for bounded random variables and independent bounded random variables, this normalized random variable here, this will be having some distribution that is not necessarily standard Gaussian. Okay, so it is critical that the sum of the variances diverge. So what does Selberg's central limit theorem look like? Okay, so this doesn't look like a central limit theorem, but this is initially what Selberg proved. So remember this function S of t. So this was the 1 over pi times the imaginary part of logarithm of zeta on 1 over 2 at 1 over 2 plus it. So on the critical line. So you look at this type of average. So this is the 2k power, right? And it turns out that when you look at the 2k power with this integral, you get some special coefficients here. Okay, so this t you can think of as being the length of the interval. So this t isn't that important. It's like a normalizing factor. And then for 2k power, you get k power of log t. Okay, and this is big OK. So this is like a error term that is up to a constant of this size. So the error term isn't that important, and it is supposedly small than the main term. Now, what is special here are these coefficients. So, when you suppose that you have a random variable that has mean 0, sorry, a Gaussian random variable with mean 0 and variance 1/2 log t, then you get the same type of term. Okay. The only difference is this pi to the 2k. But remember, pi was just a term that we had in the function s of t. Okay, so when we remove pi, we get argument of zeta at 1/2 plus it. But when we remove pi, we see, exactly the same thing here. Okay. So this is when, these coefficients, they match exactly. Okay. So what does it tell us is that this S of t, this asymptotically has a Gaussian distribution. Okay. This is because the Gaussian distribution is a distribution that is completely determined by the moments, the value of the moments. So what that means, if you have a random variable and you know that its moments are of this form, then you know that that random variable has a Gaussian distribution. Okay. So Selberg didn't realize this at the beginning. He computed these moments, and then later he realized that by computing these moments, he was actually able to say something about the distribution. So this is the distribution function for the logarithm of the zeta function. So this mu is the Lebesgue measure. So you normalize it with by dividing with t, okay? And you see this distribution function of the Gaussian random variable here, and you have some sort of error term that is not important for that for this moment. And so you see this type of thing. So log zeta, this is of course a deterministic case, but you see that we are not subtracting anything. So this tells us that the mean looks like it is 0. And then the variance looks like it is 1/2 log t. Okay. And for argument of zeta, we have a result of the same type that looks very similar. The only difference is this error term. So error term, since we look or we care about the cases where t is large, the error term here, it is a bit smaller. Okay. So this sort of tells you something about the distribution functions. Let me repeat that. So you would need to look at the measure of t for which this function here takes a value that falls into some interval AB. So this will be like a histogram of values that looks like the Gaussian bell curve as you let capital T to infinity. Okay, so you can think of it in that way. Sometimes it is written in the complex case, in a complex plane. So when you look at logarithm of zeta, then you have a complex, almost random variable, and it turns out that you sum the variances. So it was half log t. So you add those, so you get log t. And also these real part of the logarithm and imaginary part of the logarithm, they are actually independent of each other. That was also something that Selberg proved. So you basically multiply these density functions as here, and then you get this main term here. So this version that is not something that you usually see, but sometimes this is also a compact way of writing it. So what Selberg's central limit theorem sort of achieved or influenced. So prior to Selberg's theorem, it was known that this S of t, so 1/pi times argument of zeta at 1/2 plus it, that function is of size log t, up to some constant. So this is a very classical result. The proof of it is not involved. And then the only sort of slight improvement that we have is by Littlewood. So he showed that instead of log t, you could have log t over log t, but this result also depends on the Riemann hypothesis. So it is not even unconditional. So you need to assume Riemann hypothesis in order to get this sort of slight improvement, right? It's not a big improvement here. So there's a big difficulty here where it's been almost 100 years and the result of Littlewood has not been improved. Okay, so this is the best big O. This is called the big O notation. This is the best big O result that we have for argument of zeta on the critical line. So Selberg's theorem was not able to improve this, but it was able to sort of influence some succeeding results. So one type of result that we have are these omega plus, omega minus results. So what this means is that you can find a sequence of Tn that tends to infinity, where over this sequence of Tn, your S of Tn will be of this size. So basically something like cube root of log Tn. Okay, and then you can have like a positive constant that gamma plus sort of denotes that positive constant. And then on the other side, you can have like a negative constant. So S of Tn will be that negative constant log Tn type result. So S of Tn will be smaller than that. So these are of different type results. So it's not like a big O result, but the proof of these results, so the result of Tseng and the result of Montgomery, you can see some similarities to the proof of Selberg's theorem. The sort of the most strong result that we have is due to Bondarenko and Tsai. So this was more of a recent result where we now have this result for S of T. So this is going to be, so you see there isn't much improvement here, but these improvements, they come in very slowly because the proofs are very technical. So they improve this by a factor of triple log T square root, okay? And usually when you prove something for S of T, so that's the imaginary part of logarithm, sometimes you're also able to generalize that to the real part of the logarithm. And then, you just exponentiate your result for the real part of logarithm. And then you find something for the modulus of zeta. Okay, so these are just an assortment of results that I wanted to show you here. Now, another direction that one can look at is how large does the logarithm of zeta get on the critical line. So what does Selberg's central limit theorem provide us? So let epsilon be a number that is close to 0, okay? So by using Selberg's theorem, so this is the variance in that theorem, so 1/2 log t here, and then that interval that we had, AB, you can think of it as being epsilon to infinity, okay? So by Selberg's theorem, we know that this condition will hold when epsilon is close to a number that is close to 0. And since epsilon is close to 0, this number is close to 1/2, right? Because this is almost half of the full integral. Okay, so the probability of that is like 1/2. And you can also consider the opposite direction where you have minus epsilon and epsilon is still close to 0. Then that will also hold with probability almost 1/2. So you see these results are, they have to be disjoint. So when you combine both of these, you see that modulus of S of T must be something that is large. So this epsilon is some fixed number, but you can choose capital T to be large. So S of T gets really large in this size, square root log T. But this is still smaller than what we expect. So we have some conjectures that was influenced still by some probabilistic heuristics. So for example, this was a conjecture of Gorek, Farmer, and Hughes, where they think that the maximum of S of t should be square root log t, in addition to that square root log t, and we must have this 1 over pi square root 2, okay? And usually we don't have any other reason, not to expect a similar situation for the real part of the logarithm. So this is, the same conjecture for the real part of logarithm. So this pi, this still comes from S of t. And there's like a folklore conjecture. So remember, Riddlewood's result was of big O log t over log t. And some people believe that that's the size of the maximum. So this S of t becomes as large as log t over log t. Mainly because we haven't been able to improve Riddlewood's result in the following 100 years, and they expect that there will be some constancy where this type of result will be true. Okay, so either of these are conjectures, so they're just speculations. So the first one, as I said, this comes from some probabilistic heuristics. So this one is even larger than the size of the maximum here. Okay, so now let's see some important ideas in the proof of Selberg's theorem. Okay, so when you try to prove something about the distribution of a function in analytic number theory, most of the time you want to use methods of moments. And so prior to Selberg, people definitely computed some moments. So by moments, by the way, I mean averages of the kth power, averages suitably defined. So prior to Selberg, definitely Hardy and Littlewood, they studied moments of some function. But I guess with Selberg's proof of central limit theorem, this method sort of became well known. So what you do in general, you take your function. So here our function that we are interested in is this function S of t. What you want to do is you want to approximate it by something that is simple to work with. In this case, that will be a Dirichlet polynomial. So this is going to be the imaginary part of some Dirichlet polynomial, because this is imaginary part of the logarithm of zeta. And the important thing in our case is that we have a sum over the primes. This is basically because primes have some approximate independent behavior that is sort of hidden in between them. And you compute the moments of this polynomial. So we have tools to do those, to compute moments of Dirichlet polynomials. And what you do, well, you take the imaginary part of something. So imaginary part of z, let's say, is z minus z bar over 2i. So when you take the 2kth power, you apply the binomial theorem, and you get something of this form. So you get averages of these mixed terms here, okay? You can still compute these. So you will compute a jth power, 2k minus jth power. You will expand everything. And then you will compute this average here. And then when you compute the moments of your Dirichlet polynomial, then in a separate way, you show that these moments approximate the moments of S of t. So that will give you an asymptotic for the moments of S of t, and then you will be done. Because as I said, the Gaussian distribution is determined by moments. So you'll know what the distribution of S of t is. Now, the first step was approximating by a Dirichlet polynomial. Now let's see how Selberg did that. So we want to prove some approximate formula for imaginary part of log zeta, let's say, okay? because in this talk, it is easier to deal with the imaginary part of log zeta. Now, log zeta is not some easy object to deal with. So usually you start with the logarithmic derivative, and then you integrate whatever you have for the logarithmic derivative. So the logarithmic derivative of zeta can be written in this way. So this, sorry, I haven't put the definition of lambda n here. So this lambda n, this is going to be logarithm of p when n is the power of the prime p. Okay, so it will occur, it will be non-zero only when n is p to the alpha, and it will take value log p. Okay, so this is some weight that is put on prime powers. Okay, so what you do is you even sort of extend that, and then you define a weighted version of the form-angled function. So what this does is when this n is small compared to x, then this is the usual form-angled function. When n is large, so when n is between x and x to the 2, this will be a smaller weight. So what this means is when you have a prime power that is smaller than x, then you have a weight 1. When your prime power is large, you have a smaller weight. So this is basically a weight that is focused on smaller primes. That's because the distribution is determined by smaller primes. And so in this talk, we will assume the Riemann hypothesis for the proof of this, because this is easier, things are easier to see. Now, how do we prove the approximate formula for S of t? So first, the first step is to prove an approximate formula for the logarithmic derivative of zeta. So Selberg proved this type of approximate formula for this function. Now, these last two terms, these are not that important, but what is important is this first term. So this is sum over n, but remember the form-angled function, or the weighted form-angled function, it only exists over prime powers. So this is a sum over prime powers, and this is a sum over non-trivial zeros. So this is all non-trivial zeros. So you see this duality here. So there is this sort of sum over primes, right? You could ignore primes with power larger than 2. You have primes, and then you have non-trivial zeros. So they both contribute to this formula. Okay, and if you are an analytic number theorist, you may recognize this from Perron's formula. I mean, as an analog of Perron's formula. So the Perron's formula is this formula on at the bottom of this page. So that gives something for lambda n over n to the s. And you sort of compute this type of contour integral. And you can prove this formula of Selberg by using this type of contour integral. So you see the kernel functions are different here. This is a kernel that decreases faster, and it is written in a suitable way so that at the end you will see lambda xn over n to the s. Okay. So another formula that we have for the logarithmic derivative, this comes from writing an infinite product over non-trivial zeros for the zeta function. Okay, so the so-called Hadamard factorization of the zeta function. So it will turn into a sum like this. And the nice thing about this is this works for all the time for any s. And so what do we do? Well, let me show this page. So here you have this type of formula for zeta function. Now, this is good when real part of S is in a suitable range, because you have these rows, non-trivial zeros that have real part 1 over 2. So we assume the Riemann hypothesis. So this S should be close to the 1 over 2 line. But this works for all S. So it turns out that when sigma is bigger than the real part of S is bigger than 1 over 2 plus 1 over log x, you have this type of approximation. So this comes from Selberg's formula. Basically, it turns out that all those terms, they are small like this, and the sum over non-trivial zeros, it simplifies to this type of sum, and then you have this small number, some constant number C. Okay. So what you do is, so this holds when sigma is bigger than sigma 1. This holds for all S. So you compare these two at sigma equals sigma 1. And then when you do that, you see that this sum over non-trivial zeros is bounded by some constant of some constant times sum over primes. Okay, so this is an important step because when you have a sum over non-trivial zeros, it is really difficult to estimate that. Okay, so what this implies, so the sum over the zeros is decreasing in sigma minus 1 over 2. So let's see what that is. So it is this sum. So when you increase, okay, it was in the previous page, but you will have something like sigma minus 1 over 2 here. So when you increase sigma, this sum will also decrease. So what that means is that sum, it doesn't contribute much when sigma is bigger than sigma 1. So when you also take the imaginary parts, you still get, you still recover that approximation by sum over prime powers, and then the sum over the zeros, it is still small. Okay, so when sigma is bigger than sigma 1, we have a nice approximation for imaginary part of zeta prime over zeta. So when sigma is between 1 over 2 and sigma 1, so we assume the Riemann hypothesis. So this is the dangerous region, right? So we are close to the 1 over 2. So we are close to the line where we have these non-trivial zeros. So then we use the formula that follows from the Hadamard factorization. So you have a sum over non-trivial zeros. You take imaginary part of that, and it turns out that by computation you get something like this. Okay. So we are looking at this type of thing for the difference. So this because when sigma is between sigma 1 and 1 over 2, we expect that the difference is small. So it is easier to look at the difference rather than just looking at imaginary part of zeta prime over zeta, okay? Because we know what happens at sigma 1 plus IT. Okay, so now we integrate everything because we had some formulas for zeta prime over zeta, and we want to obtain some formulas for log zeta. Now, S of t, so this is the imaginary part of logarithm of zeta. This is this integral, okay? This is equal to simply this integral, because at infinity, the value of the antiderivative is 0. So you separate this integral from 1 over 2 to infinity into some pieces. You separate one piece from sigma 1 to infinity, okay? So you have another piece from 1 over 2 to sigma 1. But that piece from 1 over 2 to sigma 1 isn't very easy to deal with. So you sort of add imaginary part of zeta prime over zeta at sigma 1 plus IT, and then you subtract that in this middle term. Okay, so we have obtained formulas for this integrand, right? We know what happens here because here sigma is bigger than sigma 1. And we also know what happens at sigma 1 plus IT. So we just substitute everything and do suitable integrations. We then obtain this type of formula. So remember we had lambda xn over n to the s. So when you integrate that, you get an additional log n here. Okay. So far, this is the approximate formula that we have. The only minor disturbance that we have is that this is a sum over prime powers, not primes. So now we want to do that. So this is the same formula that I wrote before. And actually it turns out that you can show that the prime powers with power larger than 2 are, they're not very important. So you basically get something over primes. So this lambda xn, this is almost like this is almost like log n when n is a prime. So they cancel each other, and then you get n equals p terms here. Okay, any questions? Okay, so the important thing is this S of t, this is approximated by these, one of p isn't important, a sum over primes. Okay. So now what Selberg does, so he doesn't assume the Riemann hypothesis. So remember, Selberg's central limit theorem is unconditional. So what he does is he uses a different weight that is a bit more technical. So this weight extends to x to the 3, to nx up to x to the 3. It's a technical detail. And then he proves a different approximate formula for zeta prime over zeta using this type of weight. And that also comes from an integral with a different kernel that looks like this. So the difference is you see this kernel, and this has a power 3 here. So this decreases faster. So it allows him to avoid the assumption of the Riemann hypothesis. The difficulty is, again, dealing with these sum of non-trivial roots here. Okay. And then another step that he takes is he uses this sigma xt instead of sigma 1. Basically, what he does is, so suppose that you have this point sigma plus it. So if sigma plus it is close to a non-trivial 0 row, then you have to change your sigma 1 depending on sigma plus it, and you change it in this way so that sigma 1 is not very close to row. Okay. So another item in the proof of Selberg's theorem. So we have the approximation by a Dirichlet polynomial. Now we want to compute the moments of that polynomial. So again, you write this imaginary part in this way, right? So you have some polynomial coefficients, and then you have this integral over t. Now, how does this work? Well, suppose that j is fixed, okay? And then we consider some generic term here. So you have, when you expand this j power, you get, let's say, p1 up to pj, some primes. And then when you expand this 2k minus j power, you get some other primes, let's say q1 up to 2k minus j. Okay, and when you combine everything, since you have a modulus here, when you combine the term that has to do with t, this is the integral that you have to compute. Okay, and these are all, they come with power 1 over 2. Okay, so what does this tell you is, so you have something, some number, let's say a to the power it, right? So when a is 1, then you get 1 from there, right? I mean, of course, with 1 times t. So, but when a is not 1, then you know that a to the it has an entire derivative, and everything actually will be smaller. Okay, so what happens when that number a is 1, right? That means that you must have p1 times pj equal to q1 up to qk minus j. Okay, so that means your primes must be sort of equal to each other across, you know, this equality, right? So this p1, for example, it will be equal to some ql, let's say. So you will have the same primes. And what that means is when you have the same primes, you also must have the same number of primes across the equation, right? So 2k minus j must be equal to j. So that means j must be equal to k. Okay. One detail. Okay, so you have all these primes p1 up to, let's say, pk, right? Because j is equal to k. Now, you have a square root here, right? So if you want to make things large, then you will also have distinct primes. Because if you don't have distinct primes between p1 up to pk, then they will sort of form, you know, a smaller number. I mean, if you have like p1 to the 2 here, then that will make this smaller. But if you have distinct primes, in between, P1 up to Pk, then things will be larger. So this is going to be the form of the largest contribution. So P1 Pk, and this is approximately this kth power. Of course, this is not equal because you're talking about distinct primes, but the primes that are not distinct, they will end up in some error term. Okay, and this kth power, this thing inside the kth power, we know how to compute that. It's a sum over primes that is known since 19th century due to Mertens, and this is about log x, approximately, of course. And what you do is usually you choose your x in a suitable range. So in this range, a log x is about log t. Okay, so t is of our the height that we are working with. Okay, so the little t is up to capital T. So we have seen now that we have this log t to the power k. Okay, so there was also an additional term, right, where we had these coefficients that was related to the Gaussian distribution. Well, these coefficients, they come from counting the primes that sort of match each other. So you sort of choose something like 2k choose 2k factorial over k factorial, because the primes sort of are equal to each other suitably. So the 2k moment, when you work with the Gaussian random variable with mean 0 and variance 1, it is equal to this. So there is a 2 to the 2k here. And there's a 2 to the k here. So there's an extra 2 to the k, and then you put that into this log t. So you have log t over 2. That's the variance in this case. So this 2k choose k, remember the binomial factors that we had by binomial expansion. So they come from there. That's the middle term in this case. So this was the proof of Selberg's theorem. So you compute the moments of the suitable Dirichlet polynomials, right? And then that tells you something about the distribution. Now, this was Selberg's theorem, right? So when you have this distribution function, since you computed, suitable moments, you know what the distribution function is as t tends to infinity. But in addition to that, you have some knowledge about the rate of convergence. Now, how good is this rate of convergence, right? So by that I mean, can that be improved, right? Can you get a better error term here? The answer is at least probably no for now, because this is very good compared to what you will get when things are completely random. Now, of course, the case of the logarithm of zeta function is a deterministic case, right? There is nothing actually random, but it turns out that the primes have some approximate random behavior in them. So that will also bring us to the question, so why we have a central theorem for the behavior of the logarithm of the Riemann zeta function, right? Why do we even have such a theorem? Okay, so let me try to answer that. So keep in mind the Dirichlet polynomial that we worked with. So imaginary part of sum over p, where we had 1 over p to the 1 over 2 plus it. Okay, that was our Dirichlet polynomial. Now, instead of that, you can sort of construct a random polynomial. So suppose that this theta p, they are IID random variables that are uniformly distributed over 0, 1. Okay, so when you take this to your exponent of e to the 2 pi I here, so this is on the unit disk, right? So on the unit circle, so this has modulus 1. So you have p to the 1 over 2 here. So instead of that p to the it, now think of this e to the 2 pi I theta p. Okay, so this random polynomial, it approximates the behavior of the suitable Dirichlet polynomial. It's like a random model that you can think of. So we work with imaginary part here, right? This is a complex number. So we work with imaginary part so that everything is real. Now, when you look at this random polynomial, so it turns out that the mean of this random polynomial is 0. That can be computed easily, right? Because you have this e to the 2 pi I theta p, and you have uniform distribution of theta p. When you look at the variance of that, so you would get 1 over 2. So 1 over 2 will come from, imaginary part of z being z minus z bar over 2i. So there will be 1 over 2 coming. And then you will get this type of thing, this type of sum. So this is the same type of sum that we encountered before, sum of 1 over p. This is of size log x, okay? So you get 1 over 2 log x for the variance of this imaginary part of this random polynomial. Okay, so the important thing, so remember this x was, log x was like log t. So we choose x suitably so that works. So we let x to infinity, right? That's the number of random variables that we have in this sum, right? So we want to let x to infinity, and we see that when x tends to infinity, the variance of this random polynomial tends to infinity. Okay, and that means we have a central limit theorem for the sum here. Okay, so this is the central limit term that we would have, and we have an error term. So the error term that comes from some additional improvements of the usual central limit term from probability theory, but it can be shown that the error term is going to be of this size, 1 over square root log x. Okay, so we have a central limit theorem for this random polynomial, right? And remember, this is the model, random model for the Dirichlet polynomial that approximates S of t. Okay, so that's basically why we have a central limit theorem for the Riemann zeta function, for the logarithm of the Riemann zeta function. Okay, so an additional remark. So this Selberg's theorem, it holds on the critical line, right? It's true on the critical line. So this is the usual central limit theorem. So what about off the critical line? So when your real part of S is bigger than 1 over 2. So in that case, you want to have a central limit theorem, indeed. When logarithm of zeta, when you look at the values of logarithm of zeta at sigma plus it for such sigma, then you just get some probability distribution function for the distribution function of that. So remember, for the Selberg central limit theorem, we divided this logarithm of zeta 1 over 2 plus it with some variance, right? So here you don't have that, you just have some probability distribution function. Okay, so of the critical line, you don't have a central limit theorem. Oops. You don't have a central limit theorem, and that's basically because your random polynomial also doesn't have a central limit theorem when this instead of 1 over 2 here, you have something that's larger than 1 over 2. Okay. So everything is sort of consistent with what you would expect from probability. The difference is between the rate of convergence. So the rate of convergence, of course, is not as good as what you would have from the random model. Okay, but it is close enough that you don't expect much improvement over Selberg central limit theorem. So now, okay, so let me try to speak of okay, can I have an extra two minutes, please?
No problem, sure.
Okay, so I want to speak of one analog that I worked on. So these are some other analogs that I don't have time to speak about. So what I worked on was so we have the the non-trivial zeros on the critical line, supposedly on the critical line by the Riemann hypothesis. So what I was working on a shifted sequence of these non-trivial zeros. So rho plus z. So z is some non-zero fixed complex number that is of small modulus. So what happens when you look at that sequence, rho plus z, right? So it turns out that you still can recover some central midterms. The only thing is you need to assume, those hypotheses. So for example, you need to assume the Riemann hypothesis if you want to get something for the argument of zeta. As you may realize, so I need to shift rho, right? Because I cannot look at the logarithm of zeta at rho. Zeta of rho is 0, but I can shift rho, and then I can study what happens over the sequence of rho plus z. So I still have the central midterm. And what happens when I look at the real part of the logarithm? Well, then things change a bit, because now you are looking at the real part of the logarithm and you are really close to rho, right? So real part of logarithm, of course, will blow up at rho. So it turns out that when you are close to that point rho, you get some mean term, m rho z. That is not 0 anymore. So in Selberg's theorem, we didn't have this term, of course. And the variance is the same, 1 over 2 log t. And even the rate of convergence is the same. So the cost of these is a bit high. So you still need to assume the Riemann hypothesis, and you also need to assume Montgomery's pair correlation conjecture. There are some consequences of this, but I don't have time to think about that or to talk about that. So I will end my talk here, and I want to thank organizers for inviting me. So Professor Ikeda, Abbas, and Semi, for inviting me. And since I'm the final speaker of this seminar series, I want to thank the organizers again for bringing us together. Thank you.
Thanks very much for your excellent talk. Was very interesting. Are there any questions?
Well, at least I have a question. Can we get the pages that we missed? Can we get the slides?
Yeah, of course. Yeah, I apologize. I think I could have planned this a bit better, but I didn't have much of an idea, I believe, about the audience when I was planning my talk. But there are definitely other variants of Selberg's theorem that one can, I guess, recall. So there are other sequences. So I looked at rho plus z, but you can look at some other sequences where you can still hope to, well, it was shown that there are some central midterms over these sequences as well. So it was basically some sequences that look like this. So I can share the slides with you.
Yeah, it will be nice. Thank you.
So Fatma, we will also put the slides in the web page under your video also. So I mean, interested people can again watch the video and also get the PDF copy of the slides as well.
Yeah, that's very nice. Is it Boğaziçi's website?
It is in Feza Gürsey Center's website and also IPM's website.
Okay. Thank you.
Thank you. The IPM website will be announced very soon. We will making it. Okay. Will be announced. Any question else?
No question, but your talk was very technical and very advanced analytical number theory talk. I mean,
exactly.
I'm very much impressed. I mean, I should confess. Very nice.
Was very interesting.
I'm glad you enjoyed it. Yeah. Hopefully, I will have more time to talk about these. I don't know if you ever meet in person or some another time. Yeah.
So maybe I will ask you a question. Do you think this is a very vague question, but Riemann hypothesis, to attack Riemann hypothesis, such methods of probabilistic approach, or do you think they will be useful?
Your
personal opinion.
Believe, yeah, I would say no. But what I think probability theory offers is just it really helps us prove results of different type. So there are these results that even go further than the Riemann hypothesis. So it definitely helps us understand the distribution of the Riemann zeta function. But I wouldn't go as far to say that it helps us to prove the Riemann hypothesis. So in order to prove the Riemann hypothesis, there was this approach of random matrix theory. So that will be a probabilistic approach. But then I guess you can say that that approach failed. So for now, there isn't hope in order to prove Riemann hypothesis in that direction. Riemann hypothesis seems like a problem where we don't really have any idea just to prove the Riemann hypothesis. That problem seems really hard. What we do is we just work on, say like vertical distribution of the non-trivial zeros, let's say. That's a problem of a different nature.
I see.
Yeah.
Thank you.
Thanks again, and you may join me for encouraging Dr. Fatma for her excellent talk. And if there are no questions, we may finish this meeting. And just before that, I should stop the recording. Yeah.